This line graph tracks the financial trajectory of a semiconductor startup called Etched. In late July 2026, the company closed a Series C funding round at a $10.3 billion valuation. Exactly 26 days later, that line spikes to $21 billion. Hardware startups demand intense capital and face grueling production schedules, which usually keeps venture capital away from young founding teams. Yet these founders, who left their undergraduate studies at Harvard in 2022, bypassed that traditional caution to secure nearly $1 billion. The sudden influx of capital reflects a structural change in how we use artificial intelligence. The industry is moving away from strictly training massive foundation models in the lab and toward deploying them as continuous, real-time agents in production. Because these models now run nonstop, the benchmark for technology infrastructure has changed. The math that dictates success is now focused on the efficiency of the inference itself, specifically how many tokens a system can generate per watt of power and per dollar spent. For years, the market standard has been the general-purpose graphics processing unit. These chips are designed to be flexible, programmable processors capable of running any algorithm, from physics simulations to various deep learning models. But maintaining that flexibility has a physical cost. A significant portion of the silicon inside these chips is devoted to programmable registers and dynamic instruction decoders, leaving less room for the actual arithmetic units that process the AI's math. Running generative models on this generalized architecture draws massive amounts of electricity. Racks of standard servers packed densely together generate intense heat, pushing data center infrastructure toward its thermal limits and forcing systems to throttle their performance. Power availability and heat management have become the primary constraints for scaling AI. To keep generating tokens at a massive scale, the hardware requires a specialized alternative that prioritizes efficiency over flexibility. Etched engineered its Sohu hardware platform around a technical wager. They designed an ASIC that hardwires the transformer architecture directly into the silicon, physically removing the general-purpose control circuits used by standard chips. This design targets the initial bottleneck of generative modeling, the prefill phase. When a prompt is submitted, the system must process all incoming tokens simultaneously, creating a dense arithmetic requirement that typically triggers high power draw. Looking at this representation of a silicon die, you can see how Etched manages that load through low voltage inference. By keeping the operating voltage significantly lower than standard chips, the compute cores run cooler, allowing the company to pack a much higher density of processing units onto the same chip. Because power consumption scales quadratically with voltage, this small adjustment leads to a massive drop in total power drain. It prevents the thermal throttling that plagues standard accelerators when they are pushed to their maximum throughput. By sacrificing the ability to run non-transformer tasks, Etched achieves an extreme compute density. They can sustain high performance on massive architectures, like Mixture of Experts, without hitting the heat limits of a general-purpose GPU. Generative AI operates in two phases. After prefill comes the decode phase, where the model generates output one token at a time. This step is not limited by raw math speed, but by memory bandwidth, how fast the chip can fetch model weights and key value caches from memory. This network visualization illustrates Etched's cluster-scale memory. Instead of keeping memory isolated on individual chips, a high-speed interconnect links the memory across an entire rack, allowing it to operate as a single, synchronized resource. Pulling from that shared pool speeds up the sequential generation of tokens. The company claims this architecture can process Llama 70B at 500,000 tokens per second for a single user, far exceeding the throughput of standard server clusters. This speed is critical for interactive voice agents and financial models. In these environments, where response times are measured in sub-millisecond intervals, any delay in token generation directly impacts the performance of the system. In July 2026, the quantitative trading firm Jane Street received Etched's first production rack. After testing it against live workloads in their own data centers, Jane Street proceeded to lead the $700 million capital injection into the company. This deployment by a lead customer suggests that Etched's engineering results in a measurable commercial advantage in environments where execution speed is the primary competitive factor. This milestone reflects a shift in how enterprise buyers approach AI infrastructure. Organizations are no longer simply evaluating standalone chips. They're looking at fully integrated rack-level hardware. Etched delivers its hardware as frontier inference clusters. By providing the custom rack design, liquid cooling, and fleet software as a single unit, they allow buyers to secure specific performance guarantees for tokens per watt at full capacity. However, delivering these systems requires navigating the physical limits of global manufacturing. Etched relies entirely on TSMC for its 4nm silicon fabrication, which exposes the startup to global wafer allocation limits and supply chain risks. Securing a high valuation is only the first step. The true test for the company lies in scaling its physical production to meet the power demands of gigawatt-scale data centers while competing with the established supply chains of massive incumbents. Beyond manufacturing, Etched faces a foundational risk. Because an ASIC hardwires mathematical operations into the physical silicon, its performance parameters are fixed and cannot adapt to fundamental changes in AI software. Standard graphics processors are adaptable. They can be updated via software to handle new breakthroughs, allowing them to retain their value even as models change. Researchers are already exploring non-transformer architectures, such as state space models and liquid neural networks. If these alternative mathematical paradigms become the new standard, specialized hardware that is immortalized in silicon could become obsolete. Etched's massive valuation is a high-stakes bet on the future of AI research. It assumes that the transformer architecture will remain the industry standard, and that the gains from specialized engineering will stay ahead of the flexibility of general-purpose chips.